Python gives you 3 different ways to do many things at once, and picking the wrong one can make your code slower, not faster. In this video we'll walk through threading and multiprocessing for classic concurrency, then dive into asyncion's event loop, and finish with the structured concurrency patterns that make asyncio safe to use in real production code. Let's start with the 2 oldest tools in Python's concurrency toolbox, threads and processes. The key to using either one well is understanding a single piece of CPython internals, the global interpreter lock. Python's global interpreter lock lets only one thread run Python bytecode at a time, even on a machine with 8 cores. So if you spin up 4 threads to crunch through a CPU-heavy loop like this one, you won't see much speed up at all. They're all fighting over that same lock. But the guild gets released the moment a thread is waiting on something: a network call, a disk read, or here, a simulated sleep. Fire off 5 of these simulated downloads on separate threads and they wait together, so the whole batch finishes in about 1 second instead of 5. Thread sharing state is where things get dangerous. 2 threads incrementing the same counter can read and write at overlapping times and lose updates in between. Wrapping the increment in a lock, like this, forces one thread at a time through that critical section, so the final count comes out exactly right. For CPU-bound work, multiprocessing is the real fix. Each process gets its own interpreter and its own GIL, so a pool of 4 processes actually runs on 4 cores in parallel. Notice the if name equals main guard it's required, because worker processes re-import your script and would otherwise try to spawn their own pools recursively. Concurrent.futures gives threads and processes the same interface, so thread pool executor and process pool executor are basically a one-line swap. Submit your i/o bound fetches to a thread pool, collect results as they complete, and if the work turns CPU bound later, you just change one class name. Executor.map is the simpler variant, handed a function and a list of inputs, and it gives back results in the exact order you submitted them. No manual bookkeeping of futures required. Reach for this when you just want all the results once everything's done. So how do you actually choose? If you're waiting on the network or disk, reach for threading the GIL releases during those waits, so overhead stays low. If you're crunching numbers, reach for multiprocessing. It sidesteps the GIL entirely with separate processes. And whenever multiple threads touch the same mutable state, a lock is what keeps it from corrupting. Threads and processes are powerful, but they come with real overhead: context switches, memory copies, and the ever-present risk of race conditions. Next, let's see how asyncio gets I/O concurrency without needing any of that. Asyncio flips the model entirely. Instead of the operating system switching between threads, you write coroutines with async def, and a single-threaded event loop decides when each one runs cooperatively, at every await point. Calling an async function doesn't run it immediately, it just creates a coroutine object. Await is what actually drives it forward, running it until it either finishes or hits its own await, like this asyncio.sleep, which yields control back to the event loop instead of blocking. Here's a trap beginners fall into: awaiting 2 tasks back to back, one at a time, gives you 0 concurrency benefit. It's exactly as slow as calling them synchronously, about 2 seconds for 2 1-second sleeps, because nothing else gets a chance to run in between. Asyncio.gather is what actually runs coroutines together. While one task is parked inside a sleep, the event loop hands control to the others. 3 1-second tasks gathered like this finish in about 1 second total, not 3. Asyncio.create_task gives you more control than gather. The coroutine starts running in the background immediately, and you decide when, or even whether, to await its result. Here, both workers start right away, and only the awaits at the end actually block. Real async code usually needs to cap how much runs at once, so you don't hammer a server with 10,000 simultaneous requests. A semaphore does that: wrap each fetch in async with semaphore, set the limit to 3, and only 3 coroutines are ever mid-flight at the same time. By default, gather cancels everything else the moment one coroutine raises. Passing return underscore exceptions equals true changes that you get every result back, successes and exceptions side by side, so one bad fetch doesn't sink the whole batch. Not every slow operation should be allowed to run forever. Asyncio.wait underscore for wraps a coroutine with a hard deadline. If it doesn't finish in time, a timeout error is raised, and you can catch it, clean up, and move on instead of hanging indefinitely. So when do you actually reach for asyncio over the other two? Managing thousands of concurrent network connections, asyncio scales far better than threads. Just a handful of blocking calls into existing libraries. Plain threading is often simpler. And when you need to mix blocking code into an async program, you run it in a thread pool through loop.run_in_executor. Gather and semaphores get real concurrency out of a single thread. But notice what's missing. Nothing here guarantees a task you create actually gets checked on. That gap is exactly what structured concurrency closes. Level 4 asyncio is about making concurrent code trustworthy in production, guaranteeing that every task you start is actually accounted for, cleaned up, and its failures surfaced, instead of silently lost. Fire and forget tasks are a real hazard. Call create_task and never await it, and if that coroutine raises, the exception can vanish swallowed, or reported late to stare as task exception was never retrieved, long after anyone could act on it. Python 3.11's asyncio.TaskGroup fixes that structurally. Every task started inside the group is guaranteed to be awaited. If one fails, the group automatically cancels its siblings and re-raises everything together as an exception group, which you catch with the new except star syntax. Tasks can also be cancelled explicitly. A well-behaved coroutine catches cancelled error, does its cleanup, and then re-raises it. Swallowing it silently would trick whatever cancelled the task into thinking it's still running. That semaphore pattern combines directly with TaskGroup. Here, 20 fake page fetches are bounded to 5 running at once, all launched inside a task group, so you get both the concurrency cap and the guarantee that every task is awaited before the group exits. Asyncio.timeout is a context manager version of wait_for, and it composes naturally with TaskGroup. Wrap a whole group of tasks in a timeout block, and if it expires, every task in that group gets cancelled together, cleanly. For producer-consumer patterns, asyncio coordinates safely between coroutines, including backpressure through maxesize. A producer puts items on the queue, a consumer awaits queue.get in a loop, and a sentinel value like none signals there's nothing left to process. As a quick reference, TaskGroup runs tasks with guaranteed cleanup and propagation, except star handles the exception group it raises, task.cancel requests cancellation directly, asyncio.timeout cancels a whole block if it runs too long, queue coordinates producers and consumers, and semaphore caps how many coroutines run at once. That's structured concurrency. Every task awaited, every failure surfaced, every timeout and cancellation handled cleanly. Put together with threading and asyncio basics, that's the full concurrency toolkit Python gives you. That's the full arc threads and processes for classic concurrency, asyncio event loop for lightweight I/O, and structured concurrency patterns that make it production safe. Every line of code in this video comes straight from these 3 lessons on Python Mastery. Path links are on screen now.